So today's lesson will be studying states of matter and gases. So studying state of matter and gases. So when we hear the word matter, I know sometimes we remember the primary school or secondary school definition that says matter is anything that has weight and occupies space. So this definition still holds true. It still holds true. Let's see what we have. In this lecture, we'll try to see how much we can explore the properties of matter, um, like their behavior and some other properties. Usually, their behavior in different conditions, yeah, with very different conditions, and keep some other static. So that's going to be what this evening's lesson is going to be about. It's going to be basically about matter and some of the laws that govern the behaviors of matter. So we'll also look at the kinetic theory of gases. We'll talk about ideal gas and real gases. I don't know whether there's any lesson I've taught about ideal gas and real gas before, but we'll be having that today. And we'll also try to learn about the Van der Waals equation and its implication, or when it is being applied. So let's head into the lesson for today. First off, I'll start by explaining what a phase diagram is. A phase diagram. So a phase diagram is actually a graph that tries to show the different states of water or the different states of water, or the tries to show water in its different state. I don't know. I thought I imported the image here. I don't know where I imported that image. The image for the phase diagram of water. But there is a diagram. I don't know how it is, but maybe I'll send it after the group, after the lesson. I'll send it to the group. I just hope I remember. I'll send the phase diagram of water on the group. So it's a diagram that looks like a symbol Y. So it looks like a symbol Y, where each portions that are being enclosed by two lines represent different phases of water. So while the center point of that Y is seen as the triple point. So usually it's just something like this. Something like this. You have something like a Y-shaped graph, one going like this, and another one just intersecting it. So where each of these portions that are by the sides, they represent different phases of water. So the center is always representing the center of that Y, that center of that meeting point, the junction is known as the triple point. So this graph, what it tries to show is how it's a graph that tries to show the relationship between pressure and temperature. Pressure and temperature. So how water's phase vary with pressure and temperature. So that's what the phase diagram is about. So if you're writing, you write that the phase diagram, is a graphical plot that tries to illustrate how water changes from one phase to another with varying pressure and temperature. So it's a graph that tries to show how water changes in states from solid, liquid, or gas as pressure and temperature changes. So that's what this graph is about. So the key feature of this graph is the triple point. So triple point, as I said, is the center point. So as me, you had a Y symbol. The center of that Y is on the phasor diagram. On the phase diagram, is called the triple point. The triple point. So that's the point where that pressure and temperature at that point, whenever that pressure and temperature is met at the same time, water would exist as both solid, liquid, and gas. It will exist in those three phases. So that's what the phase diagram shows. So the graph, the line that is between solid and liquid, is one that represents the conversion from liquid to solid or solid to liquid. The one that is between liquid and gas is also the same way. But this explanation, I think, it will be more it will be clearer when you've seen it, or when you are seeing it physically, or when you are seeing the diagram. So now, that's typically what phase diagram of water is about. It's about how. Hello, can you guys hear me?
Yes, sir.
Hello, can you guys hear me? Okay. So the phase diagram, when you hear the phase diagram of water, it's just a graphical representation that tries to illustrate how water changes phase from solid, liquid to gas, and the points, which are known as the critical points and the triple points. So the critical points is where liquid and gas phase become indistinguishable. So that's when you hear the word critical point. It's that point where it's difficult to distinguish between liquid phase and gaseous phase. So let's see. We talked about, decided in this lesson we're talking about the properties of matter. So we've talked about matter. Matter is anything that has weight truly and occupies space. And we have three major states of matter. We have the solid state, we have the liquid state, and we have the gaseous phase. So the solid state of matter is when the atomic force, the interatomic forces are strong, and also the intermolecular force is also strong. So we have two forces, the nucleic force or the nuclear force holding the electrons together, and we also have another force that is also holding each of the atoms together, which is the intermolecular force. So for solids, the two forces are strong, but for liquid, the intermolecular force is not that strong. So it's only the molecular force that is only it's only the nuclear force or the innermost energy or force that is more pronounced. So simple, I'm just trying to put it in simple terms. It's just like as though in solids, there are more forces holding the particles of solids together. In liquid, they reduce by one. While in gas, there is no force holding the particles together. So that's why the gas molecules or gas particles always want to spread as far as possible, so long as they see space. So these gases, we've heard stuff about ideal and real gas. So is when you hear the word ideal and real gas, for solid have a particular behavior or property, but that's not for this lesson. Liquid also have their own behavior and property, and that's also not for this lesson. So we'll be zooming on just gases. So for gases, we have two types of gases, or two basic type of gases. We have the real gases and the ideal gases, where the real gases are gases that deviate from ideal gases. So these ideal gases, on the other hand, they are gases that are assumed to have some special characteristics. So when we go to kinetic molecular theory, I would explain this in broader detail. It's in this lesson, but I'll explain it in broader detail. So now we are now here trying to see the relationship between pressure or the properties of gases and what is responsible for these properties of gases. So one of the first property of gas, or one of the first principle that tries to govern the behavior of gases, is called the Boyle's law. It's not really a principle, it's not really a theory, it's a law, because it applies true at every single point. So what this Boyle's law tries to explain is that it tries to state that pressure of any gas is inversely proportional to its volume at any constant temperature. Meaning, when you try to increase pressure, the volume of a particular gas will continuously decrease as long as you increase pressure when the temperature is constant. So there are three parameters that have been mentioned in this Boyle's law, and it's important that once you are memorizing the Boyle's law, you memorize these three parameters: pressure, volume, temperature. So in Boyle's law, temperature is constant. First thing you should know, in Boyle's law, temperature is constant. Under constant temperature is for Boyle's law. So, but now you're not trying to see the relationship between pressure and volume. Since temperature is constant, pressure and volume are the ones that are left to vary. So now what can happen is you can either increase the pressure and see what happens to the volume, or you decrease the pressure and see what happens to the volume. So there is an inverse relationship, meaning when you increase pressure, volume would decrease. When you decrease pressure, volume would increase. So this is for all gases. This is the principle that governs all gases. So that's the expression of Boyle's law. So as a result of this definition that is inversely proportional to volume, the graph is usually an inversely sloped graph. An inversely sloped graph. The graph of Boyle's law is usually an inversely sloped graph. So, and it is given by the formula P directly proportional to 1 over V, representing the inverse proportionality. Representing the inverse proportionality. So for what they call this stuff, for now, questions, how questions come out in under this topic is you would see that it will give you a system. There are barely questions that will come out like this directly as direct as this, but they usually will come out as a combination of other questions. So, but when you have more than one gas condition, or when a gas condition changes over time, you then use the pressure formula, that the Boyle's law formula that is given differently. So I'll try to explain this. The Boyle's law formula is given by P is directly proportional to 1 over V, what we have here. P directly proportional to 1 over V. So when you then try to remove the constant of proportionality, you have P is equal to K over V. P will be said to be equal to K over V. That's for Boyle's law. And it's when you have different or changing pressure or changing volume, the formula becomes different. The formula becomes P1 V1 equal to P2 V2. That's what the formula becomes. P1 V1 equals to P2 V2. That's the formula for Boyle's law when you have changing pressure and changing volume. P1 V1 equals to P2 V2. So now let's move on to the next we have. Next we have is Charles's law. So Charles's law is another of the popular law that we've known so far. It's related to Boyle's law. Whenever you hear Boyle's law, usually your mind should go next to Charles's law. So this Charles's law is still similar to the Boyle's law, but there are some tweaks between Charles's law and the Boyle's law. So for the Charles's law, we are still considering 3 parameters: pressure, volume, temperature. The same with Boyle's law, pressure, volume, temperature. But now for Charles's law, we assume that pressure is constant. For Boyle's law, we assumed that volume is constant. But for Charles's law, we assume that pressure is constant. So when pressure is constant, according to Charles's law, it says that when pressure is constant,
please excuse.
the volume.
Sir, wait.
Yeah,
Sir,
I can hear you.
Sir, as Boyle's law, I thought that temperature is constant, not volume.
Did I say volume? Sorry. For Boyle's law. Sorry.
It says volume.
Sorry, you're correct. For Boyle's law, I made mistakes. So in my head, I was saying temperature. In my head, I was saying temperature, but I did not know I was saying volume outside. So for Boyle's law, it is a relationship between pressure and volume. So temperature is meant to be constant, but temperature is assumed to be constant. So, but for Charles's law, it's a relationship between volume and temperature, while assuming that pressure is constant. So for Boyle's law, temperature is constant. For Charles's law, pressure is constant. So that's how this relationship, that's how you compare between Boyle's law and Charles's law. So for Charles's law, they assume that when the pressure is constant, the increasing the volume of a particular gas will also increase the temperature of that gas. According to Charles's law, that once you increase the volume of a particular gas, the temperature of that gas would also increase. And when you decrease the volume of a particular gas, the temperature of that gas would also decrease. So that's what this law is stating. So that's what this law is trying. Jesus. Hello, can you guys hear me now?
Yes, sir, we can hear
Hello?
you.
Yes.
Okay. So now, as I was saying, I said for the Charles's law, they assume that as you change temperature, if you increase temperature, volume would also increase. And if you decrease temperature, volume would also decrease. So that's the relationship for Charles's law. So for Charles's law, it is the relationship between volume and temperature, seeing how their proportionality works. So for Charles's law, there's a direct proportionality between volume and temperature. For Boyle's law, there is an inverse proportionality between pressure and volume for Boyle's law. So now, the formula for Charles's law is given basically as V directly proportional to T. V directly proportional to T. So then when you have changing volume and changing pressure, the formula becomes V1 over T1 equal to V2 over T2. And the reason for that is because when you try to bring all the V and T on one side, it will be giving you V over T equal to K. So when it does not mean that they are constant, when it means that they are varying, when the pressure is varying, temperature is varying, it means V1 over T1 will then be equal to V2 over T2. So this is the mathematical expression for the Charles' law. So typically, questions that will come out from this topic would usually be a masked kind of question, like a masked question, where you'd have something like a mixture of Boyle's law and Charles' law, or a question where you don't even mention whether you should find whatsoever. They'll just tell you the question in a tricky way. They'll tell you, okay, assuming we had a gas cylinder, and the temperature of the gas cylinder seemed to have risen from 25 degrees Celsius to maybe 100 degrees Celsius. What will be the volume of the gas? So these are that's the question. So I have a question to ask you guys. Can you guys hear me?
Yes, sir.
Yes, sir.
Hello. Okay, so I have a question to throw on you guys now. I would need someone that's probably sure of what they're saying to give me an answer. So what happens if I had a gas cylinder without calculating? If I had a gas cylinder and someone started heating up, or the room started, there is now heat in the room, and the heat in the room begins to increase. What will happen to the quantity of gas in that cylinder, or the volume of the gas in that cylinder? Still, I have a gas cylinder, and we start to heat up
Please,
this
can you
gas
repeat?
cylinder.
Sorry.
What would happen to the volume? Yeah, I can hear you.
Can you like repeat the question? I didn't hear your voice
Yeah,
was cracking when you were saying it.
okay, so the question is this: assuming you had a gas cylinder, no, not you, assuming someone had a gas cylinder, and the gas cylinder, they started heating up the gas cylinder from the bottom. What would happen to the volume of gas inside that gas cylinder? What
The
would happen to
temperature
the
will increase.
volume of gas inside that gas cylinder as time goes by? Yes, I'm saying that we increase the temperature. That's what I'm saying. We are increasing the temperature. So what will happen to the volume?
The volume will decrease.
They said the volume will decrease. Does anybody support this her opinion, or does someone have a contrary opinion that when you increase the temperature of gas, maybe something would happen to the volume of the gas? What would happen if you have an idea, or if you feel you can say something, or you have a contrary opinion to what she said? She said when you increase that temperature, is that the volume of that gas will begin to reduce. So does someone have any alternating opinion, or
I
any
think
opposite
it's
opinion?
reduced.
Okay, that when you increase the temperature, the volume of the gas will reduce, right?
Yes, sir.
Okay. Okay, does anybody have any other contrary opinion? Any other person? Before I give the answer, so we'll know whether she's correct or she's wrong. Okay, let me give the answer straight up because of time. So in real sense, according to the Charles law states that the volume is directly proportional to temperature. So what does directly proportional mean? What does that sentence or that phrase, directly proportional? What does it mean? It means as you said.
It's going to increase. It's going to increase.
So that's the correct answer. The answer is that it would increase because, according to Charles' law, whatever you do to volume, it would affect temperature positively. The same thing you are doing to volume would also be happening to temperature, according to Charles' law. That's why he said they are directly proportional. Meaning, if you increase the volume, the pressure would also increase. Or if you decrease the pressure, the volume would increase as well. So that's what Charles' law states, and that's the answer to the question. That once the temperature is increased, the volume of the gas would also increase. So this is the reason why gases explode. This is the reason why gases explode, because the temperature within when you are started heating of the gas cylinder, the temperature begins to increase. and the gas molecules will begin to receive more energy, and they would want their collision with the wall of the vessel will become more. Their kinetic energy would increase, and as a result of that increased motion force and continuously increasing temperature, it will get to a point where the gas molecule will have enough strength for them to expand and burst the gas cylinder. So that's what we see as explosion. So that's what happens when you increase temperature of gases. The volume would increase as well. When you increase temperature, the volume would also increase. And that is the practical example that tries to explain it. I don't know if anyone got my drift.
Yes,
Yes,
you were trying to explain
understand, you understand.
what directly proportional. So please go on and explain
Yeah,
it. Thank you, sir.
yeah, I just explained it already. I just explained it. So direct proportional mean that as the volume or as one of them is increasing, the other one will be increasing as well. Or as one of them is decreasing, the other one will be decreasing as well. So it does not matter which of them is increasing or decreasing. Well, so long as one is increasing, the other one will increase because of their direct proportionality. But when they say that they are inversely proportional, whenever you hear that two parameters or two entities are inversely proportional or they have an inverse relationship, it means as one increases, the other one will decrease. As the other one decreases, the other one increases. So it's like as if they are opposite. They are opposite. So for Charles' law is talking about volume and temperature. So he said that they have a direct proportionality. Boyle's law is talking about pressure and volume, and he said they have inverse proportionality. So meaning, according to Boyle's law, if the pressure of a particular system is being increased, the volume of the gases in that system will begin to reduce. It will begin to reduce. So let's move on to our example. Here we have said a gas at 0 degrees Celsius occupies a volume of 2 liters. What would be the new volume of gas, the new volume if the temperature increased to 100 degrees Celsius? So now this question is trying to apply the Charles' law, because Charles' law is one that tries to explain. Hello, can you guys hear me?
Yes.
Hello. Okay.
Yes, we can hear you.
So it's Charles' law. Okay, it's Charles' law that we will use for this question, because Charles' law is
Your
one that
voice is not
involves
audible at all.
temperature.
I just put it inside my ear before I can hear you. I've off my distance time with that number in order to see if I can hear you better or to know about.
Okay, I'm sorry about that. I think sometimes if network starts glitching, sometimes to make it look like as if the voice is mumbling or something like that. But I'll try to see how much I can do to increase my voice. So now, as I was saying, we have an example where they gave us the gas, their temperatures 0 degree and 100 degrees Celsius. And they also gave us volume, 2 liters, and they said we should find the other volume. So now, once you're giving questions under these cases or this kind of question, just write down your parameters so you'll be able to know which of the formulas would apply best. So we've seen that they're giving us volume and temperature. So meaning that we'll be using the formula that relates with volume and temperature. So as when they give us pressure and volume, we'll know we're using the formula that relates to pressure and volume. So it's that simple. There's nothing, it's not really any rocket science. So just to apply the formula, place in your parameters, and you get your final answer. So if you should solve this, your final answer should be giving you 2.73 liters. 2.73 liters. So let's see what we have next. So next is the Avogadro's law. The Avogadro's law. So we've talked about Boyle's law, we've talked about Charles' law, and we've talked about the parameters that are involved in Boyle's and Charles' law. So there's another law that is governing the behavior of gases, and that law is called the Avogadro's law. And this Avogadro's law is it tries to state that the volume of gases or the volume of a particular gas is directly proportional to the number of moles of the gas. Meaning, since we've heard directly proportional, we can, at the top of our head, say yes, meaning that as volume increases, number of moles would also increase, or as number of moles increases, volume would also increase because they have a direct relationship. So that's for the explanation. So now let's see what an example or a typical example under this would look like. So we have an example that said, if 2 moles of gas occupies 10 liter at a constant temperature, how many liters will 3 moles occupy at that same gas at the different temperature? So the formula, they could use the formula to get out the number of moles, they could use to get out the volume, but the main thing is just knowing the formula. The formula is V direct proportional to N. That's what we see here. V direct proportional to N, as you can see here. Then when you rearrange it, you can see something like V over N. So when you have 2 volume and two changing number of moles, you then use V1 N1. V1 over N1 is equal to V2 over N2. Is equal to V2 over N2. I don't know if anybody's following.
Yes, sir. But the calculation
Yes, sir.
seems confusing.
Okay. So now, the same way we had Charles's law, and we said Charles's law, because of the direct relationship, the formula is V direct proportional to T. But now, when you have changing volume and changing temperature, the formula will then become V1 over T1 equal to V2 over T2. So now, in the same way we have for this Avogadro's law, we have the volume is direct proportional to number of moles. The same way volume was direct proportional to temperature. So now, for that, we'll then be having, if the volume or the number of moles is changing, if the volume is changing or the number of moles is changing, the formula will then become V1 over N1 equal to V2 over N2. V1 over N1 equals V2 over N2. So that way you can be able to know your V1, know your N1, also be able to know your V2 and also know your N2. So that's the formula that they use here. V1 over N1 equals to V2 over N2. So plugging the parameters that we are given into the formula, we'll be getting a final answer of 15 liters. So that's meaning when you increase the number of moles in a particular system at constant temperature, what would happen? When you increase number of moles, the volume would also increase. So that's what this law tries to point out. I don't know if you figured out the solving. The final answer is supposed to be 15 liters. So if you got it correctly, then you can give yourself an award for that. So now let's see whether we can move on to the next.
Hello, sir. Sorry, sir. Hello, sir.
Yeah, I can hear you. Yeah, I can hear you.
Please, can you explain the calculation, please? Can you explain it very well?
So from the question we have our N1. Our N1 is 2. Sorry, someone's this thing is turned on. Someone's mic is turned on. Please, could you turn it off, please, so that we can hear it? Probably when you want to talk, you can turn it on back. So from our question, we have our N1, 2 number of moles. Our V1, 10 number of moles. So we've gotten our V1 and our N1. So that's what we have as V1, N1. So 10 over 2 equals to our V2. We're looking for the volume because they asked us to look for the volume. Then we have our N2. So we don't know our V2. We're looking for our N2. We don't know our V2, but we have our N2. So now putting that in the formula, we're having 10 over 2 equals to V2 over 3. So if we cross multiply and make V2 subject to formula, we'll be having V2 being equal to 10 times 3 divided by 2. So if you should solve that already, from what I said now, you should be able to get your answer as 15. I don't know if it's clear now.
Yes, sir.
So I have something to say. You know,
okay, I'm listening.
You know that JUPEB is a advanced level. is A level.
Yeah.
So all
Yeah.
these formulas they're giving us is elementary formula. So
Okay.
JUPEB exam, they will not, if we write the question like this, they won't accept it. Like that of Avogadro, the question is equated to arrow NT. That arrow is constant. Avogadro's constant. So
Okay.
it's equated to it. So I don't know whether you understand me. So if we
I
just
understand.
anything like V1 over N1 equals to V2 over N2, they won't accept it from us. No.
Okay. There is where that formula R equals to, V equal to Rn. There's a formula that is that. So the time you use this formula, this V1 over N1 equals to V2 over N2, is when you have changing volume with changing number of moles. That's also the time you use pressure, P1 over V1 equals to P2 over V2. That's when you have changing number of pressure and volume. That's when they say the pressure changes from one volume to one pressure to another pressure. That's when you would invoke that formula. In some cases, you might need to combine both Charles' law and Boyle's law, where you have P1 V1 over T1 equal to P2 V2 over T2. So that's when you have changing pressure, volume, and temperature. So these cases are when you would have, when it's only one pressure they're giving you, and they're asking you to find temperature or find the volume at that pressure, you can use that formula that we just mentioned. You usually use the normal general gas law, PV equal to nRT. That's the formula you would use, because you would then use your pressure, use your volume, use your number of moles, and use your temperature. Then R is the constant. But in the case where there is changing of these parameters are changing, the R is going to cancel out the R, and that's why you'll be left out with this. So Avogadro's law, see, if you see what I wrote here, I said the formula is this. The formula is this. This is the formula for proportionality, V direct proportional to N. So, but when you rearrange it, you'll be having V over N equals to constant. So that constant now is the R. That constant now is the R, but sometimes it's not just R, it's R and some other parameters. So that constant now can be seen as R, but most times it's not just R, but it can be merged with other constants. It can be relating with pressure and some other stuff. So I don't know whether I've communicated something to you. It's only when you are giving changing pressure or changing volume or changing, that's when you start reasoning the formula that you use P1, V1 or V1, T1 or all those kind of stuff. When you start having V1, V2, T1, T2 is when you have things changing, either volume changing, pressure changing, temperature changing, number of moles changing, then you can bring in each of these formulas individually. But when they are not changing, they're just trying to tell you, okay, the pressure of a particular gas is this, and it has a volume of this. If the temperature is this, what is the number of moles? Then you can use that P1 PV equal to nRT. Or maybe they will tell you if the pressure or if the number of moles of the gas is 3, what is the volume? You will then use V over N equal to R. You can then rearrange it and get your V. They can tell you using Avogadro's number. So that is the case when you use those simple formula, or that formula that does not have subscript 2 or subscript 1. But when you have changing parameters, let's say the same thing changes from one temperature to another temperature, or one pressure to another pressure, or volume to another volume, that's when you use these formulas in this pattern, because the formulas are still the same. They're not changing. It's just that the question is changing. So it's not that I'm omitting the way it's supposed to be. I'm just trying to state the basic form, like the way it's supposed to be, the real basis of the question. So depending on how the question then goes forward, it will then tell you how you would manipulate the formula to get your final answer. I don't know whether I've said something or I've tried to clarify you on that.
Yes, sir.
Okay. So I think maybe as I was saying, I said most likely towards the ending of this thing, we might have to go into practical questions, like real exam questions, like real questions. We might get to those points, but for now, we're just trying to finish the syllabus or try to see how much we can go with the syllabus, such that we know everybody has a general, like a grounded knowledge on each of the basic concepts. So when we then have the basic concept, we can now use it to try questions. So let's go forward to Dalton's law. So Dalton's law is another formula or is another law that tries to govern the behaviors of gases, that tells about the behavior of gases. So if you've noticed, we've been talking about laws. I hope you guys are aware of the difference between laws and theory. I just want to assume that you guys are aware of the difference between laws and theory. So it's not a mistake. When they say something is a law and they and they say another one is a theory, they don't mean the same thing. Laws and theory don't mean the same thing. Laws mean something that it's has been proven not to change. It does not change. Wherever you see any gas, whatever condition it is, so long as this and this and this are met, this law would hold true. It's a law. It's a general law. It's nothing can change it. So, but theories are the ones that have conditions where they apply specifically. But if some things change, they will begin to deviate. Like what we'll see later in this lesson, we'll see the kinetic molecular theory. It's not called the kinetic molecular law. It's called the kinetic molecular theory because of the reason that at some cases it does not apply, or in some cases it does not apply, or in some kind of gases it does not apply. But these theories, these laws, they apply in every kind of gas. So moving on, we have the Dalton's law. So this Dalton's law is also called the Dalton's law of partial pressure. And the law states that the total pressure exerted by a gas mixture is the sum of the partial pressure of individual gas, meaning the total pressure that you would see a mixture of gases exert is equal to the sum of their individual partial pressures. So that means the total pressure is equal to the sum of all the partial pressure. That's the simple explanation for it. So meaning if you have a mixture of gas A, gas B, gas C, if you have them in a single system, if you want to check for the total pressure in that system, you add the pressure from A, the pressure from B, the pressure from C, and sum it up together. You take them, sum them up. It will give you the pressure for the entire material. So let's see what the equation looks like. The equation has P total being equal to P1 plus P2 plus P3 up until Pn, where n is any number, any integer number. So now, let's see how examples come up on this topic. It said if a container contains oxygen, nitrogen, and helium gases with partial pressures of 2, 3, and 1 atmospheres respectively, what is the total pressure? So this thing is just off your head. You should be able to get the answer because it's just an addition. Just an addition. Complete addition. Just add. Just add all the individual partial pressures. So let's see, the way we solve this now is the same thing I just explained. We have total pressure being equal to this plus this plus this. So to give you the total pressure. So in some other cases, you might see that they would twist the question not to be straightforward. They might twist the question not to be straightforward. They will try to bend the question in a way that will try to give it a different interpretation. So this is basically the formula when you hear of partial pressure. This is basically the formula you would use. It's basically the formula that you would use to get the partial pressure of systems containing a mixture of several gases. So now let's see. Another law we are treating that governs the behavior of gas that does not change is the Graham's law. The Graham's law. So this Graham's law states that the rate of diffusion of gases is inversely proportional to the square root of the molar mass. So if you look at it now, they're talking about inverse proportionality. So when you hear inverse proportionality, your mind should go straight off that, okay, these gases, as one of the parameters is increasing, the other one will be decreasing. Or as the other one is decreasing, the other one will be increasing. So from this principle, we say that diffusion, as the speed at which diffusion occurs, as it begins to increase, the square root of the molar mass will also begin to decrease. Begins to decrease. If it increases, it will decrease. While if the other one decreases, it will increase. So the mathematical expression for this formula is from the formula, we're talking about rate and molar mass, or square of molar mass, or square root of molar mass. Rate and square root of molar mass. That's what the Graham's law is talking about. Weight and square root of molar mass. Weight and square root of molar mass. So those are the two rates, rate, not weight, rate. So those are the two things that are involved in the formula for the Graham's law. So now the formula is then given as rate R1 over R2 is equal to is equal to the square root of M1 all over M2, where the square root covers both M1 and M2, covers both M1 and M2. So this is the mathematical expression for the Graham's law. So it is rate, or you might see some places, so it's R over R1 over R2 equal to, then they'll put something, root of that particular molecular mass over the other molecular mass under. So it can be root M over root M2 over root M1. So take note of this formula now. Take note of this formula. The formula is rate R1 over R2 is equal to M2 over M1. So here it's 1, 2 on one side. Here is 2, 1 on the other side. 1, 2 on one side, 2, 1 on the other side. So you will not make a mistake and probably write what is not correct. So it is 1, 2 on one end, 2, 1 on the other end. Let's see how examples come out for this. If the diffusion rate of gases, or if a gas A is 1.5 times faster than gas B, what is the ratio of the molar masses? What is the ratio of the molar masses? So we already know that this is the formula we are going to be using. This is the formula we are going to be using. So now we need to state out our parameters that we're given. They gave us only the rate of diffusion for one gas, seemingly for one gas. So now, but what they gave us now is not just for one gas. They gave us an important information. They said, if the diffusion rate of a gas, can you hear me? Hello, can you guys hear me?
Yes.
Yes, sir.
Hello. Okay. So if the rate of gases, if the rate of diffusion in gases of a particular gas is 1.5, say it is 1.5 times faster, meaning we don't really know the rate of diffusion for this particular gas, but whatsoever it is, the other one is 1.5 times faster than it. So meaning we can put that rate as, we can say that R1 is equal to R1. We don't know what R1 is, but R2 is equal to 1.5 times R1 because it is 1.5 times faster than R1. So 1.5 times R1. So putting that inside your formula for your R2 and your R1, you'll be able to get a simplified formula that will look like that you'll be able to get your final answer from. Be able to get your final answer from. I don't know if anyone is talking in this point. Can you guys still hear me?
Yes, I can hear you.
Okay, I don't know. It seems like I'm thinking maybe my network is disconnected. I don't know. So now for this solving now, we don't know our R1, we don't know our R2, we don't know our molar mass of one, we don't even know the molar mass of the other one properly. So, but we're trying to find the ratio between M1 and M2. That we're trying to see what M2 over M1 would be. So now let's see. For our R1, we don't know what R1 is. So R1 is still also the same as R1. But for our R2, they said R2 is 1.5 times the value of R1. So meaning you can get the R2, or you can get your R, you can just assume that your R1 is 1, or you can cancel that R1 because you'll be having something like this. You'll be having R1 over R2, where R2 is equal to 1.5 R1. So R1 will cancel out the R1 above. So you'll be left with 1 over 1.5. So equal to square root of M2 over M1. Square root of M over M1. So that's what we can see here. We can see that here. Because when they remove the square root sign, you are left with M2 over M1. So removing the square root sign is that you take square inverse of both sides. Take square inverse of both sides. So when you solve this, you should be getting your final answer to be 44.4%. That should be the ratio between A and B. So that should be your final answer. So let me move on to the next slide. Next slide is Gay-Lussac's law. For the Gay-Lussac's law, the law states that the pressure of a gas is directly proportional to the temperature at constant volume. So in this case, you're talking about pressure. You're talking about pressure and temperature. Boyle's law talks about pressure and volume. Charles' law talks about volume and temperature. Avogadro's law talks about volume and number of moles. Graham's law talks about rate and square root of molar mass. Then now, Gay-Lussac's law now is talking about pressure and temperature, and said that the relationship between pressure and temperature is direct relationship, to mean that this is what we have, P direct proportional to T. So we will treat it the same way we treat our Charles law, our normal Charles law. So they gave us a question. They said if a gas is heated from 300 Kelvin to 600 Kelvin, and its initial pressure is 2 atmosphere, what is the final pressure? So we have our formula. We can put our formula. We can put our formula as P1 over T1 equals P2 over T2. So putting that into the formula, you'll be able to get your final answer for the final pressure that we asked for. I don't know if anyone has any questions so far. Okay, I would assume that we don't have any question. So now moving on to the kinetic theory of gases now. We are done with all those laws now. So we are now in the kinetic theory of gases, or the kinetic molecular theory. So now this theory has three major assumptions. So the first is that gases have constants, they are constant, and they have random motion. They're constantly in random motion. That's what the first assumption of the kinetic molecular theory states. It says that gases are said to be in constant random motion. That's the first assumption. And the second assumption is that elastic collision, there's always elastic collision between the gas particles and the wall of their containing vessels. That's meaning when they collide with the vessel, the wall of their vessel, they don't really reduce energy at all. Normally, when you throw a ball to the wall, or when you roll a ball towards a wall without much energy, it will get to a point where as the thing goes towards the wall, it will hit the wall and stop there. Normally, that's because of the collision between the wall and the ball is inelastic. So as means it was elastic, as the ball touches the wall, with the same force it used to come, it would also use that same force to go backward. So they assume that for gases, they have this behavior, that they have elastic collision, meaning that the collision between the wall of their containing vessels is completely elastic. So for the third theory rather, is stating that the average kinetic energy of particles is directly proportional to the temperature. So the third theory tries to propose that kinetic energy is directly proportional to temperature. It tries to propose that kinetic energy is directly proportional to temperature. So these theories together, all putting them together, is what we have, or what is called the kinetic theory of gases. We call the kinetic theory of gases. So the theory helps to explain how gases they vary and their behavior changes with changing pressure and changing temperature at specific pressure and temperature. So I think I remember saying in one of my classes, I said something like, okay, I don't think it's in this, I don't think it's here, I don't think it's in this class. Well, gases, they are assumed to, according to kinetic theory of gas, they are assumed to have constant random motion. That's one of the first assumptions. Second assumption is that they have elastic collision. And the third is that kinetic energy and temperature is direct proportional to each other. There's a direct proportionality between kinetic energy and temperature. So now let's explain real gases and ideal gases. I think we've started getting towards the end of this lesson. So ideal gases, we already know ideal gases, they are gases that seem to obey the kinetic molecular theory. So these ideal gases now, they are gases that they obey these laws or these theories that we mentioned. They completely obey it. So this is the kinetic molecular theory, and they are parts of the kinetic molecular theory. When you talk about kinetic molecular theory now of gases, now you talk about the negligible volume of gases and some other stuff. I think I've mentioned this in one of our classes, but these ideal gases, they are said or they are known to obey this theory. They are known to obey this theory. So, but at some point, it noticed that some gases don't obey this theory. And these gases that have not been known to not obey this theory, they are known as real gases. Real gases are those gases that are said not to obey or that are found to deviate from the normal behavior of ideal gases. Ideal gases, they are assumed to obey the kinetic molecular theory, while real gases, they are said to obey it to some extent, but then deviate at some other point. So the points that they deviate at is two. There are 2 points
So
that
I
real gases
didn't get
deviate.
you, please, sir.
Okay. Ideal gases are gases that completely obey the kinetic molecular theory of gases. They completely obey every single theory or every
Which
single
one?
aspect of ideal gases.
See, I'm a bit confused. This ideal gases, is
Yeah.
it both Charles? In fact, I don't understand which one is ideal gases.
Okay. I know that probably you are trying to relate ideal gases with the ideal gas equation. So first, there is what is called an ideal gas before you come to the ideal gas equation. So in the ideal gas equation is when you combine Boyle's law and Charles' law with Avogadro's law. When you combine all three, you'll be able to get the ideal gas equation. That is that PV equals to nRT, that formula. So that's the ideal gas equation. But now we're not talking about this ideal gas as a
Someone will
specific
combine
gas.
Boyle's law, gas law, and what?
When you combine Boyle's law, Charles' law, and the Avogadro's law, you would have the ideal gas equation. When you combine those three equations, you have the ideal gas equation. So then now looking at this,
Which one is ideal? Which are the ones that are ideal gas?
So that I'm trying to explain now. I need to explain what an ideal gas is. So let me leave all this talk. Let me try to bring it down to a relatable level. So now there are these people, there's this country, these people that they call that they said that all of them in that country, they have the same height. They have the same height. Nobody, both girls and boys, they have the same height in that country. The country, they said the country's name is IG. That's the name of the country. So there's a country that they said in this world that they said this country, everybody in that country, even newborn baby, if they give birth to a newborn baby, the newborn baby will have that exact height. It's the adults. They will born newborn baby at the same height. So this is what they said in that country, in the country of IG. So, but in real sense, in other countries that we are seeing that true, people usually have that particular height, but now it's not the same at every time. Some people in some countries, they are short, while some people in some countries are tall. Or let me not even use height, let me use complexion. They said in a particular country, no single person, you can never see a black man in that country, is completely white. No single person, you will not see any black person in that country, is always white. So that's the IG country. So, but in real life, no matter how you want to mention it, know how you would definitely see a white man, a black man in any white man country. There might be few, but in some areas, like in UK, there's an area that is dominated by black people. In US, there are areas that are dominated by black people. So that way, we know that truly, there are states that are that they have dominant white people. But it does not mean that that state is completely belonging, that there is no black person in that country. There is going to be, there may be few black people in some areas, but majorly we have white people in that area. So that's how ideal gas and real gas, they are somehow like, so ideal gas, they assume that ideal gas, they are very, they are a particular type of gas that they are unique. They are not heavy, they don't have any weight at all. And also, they don't have what they call it. They don't have any weight, and they don't usually occupy space. They don't behave like matter. They don't have weight. They don't occupy space. And also, they said that there is no attraction between them, between the gas molecules. So now, for ideal gases, the simple definition is that they said ideal gases, they are gases that they don't have any attraction for themselves. They don't have any force of attraction for themselves. And also, they don't have any reasonable size. The particles of these gases, they don't have any reasonable size. Their size is very tiny. You cannot even, their size is insignificant. They don't have any size at all. That's what ideal gases are. So now, but in real sense, there are some gases behave in that way. Most gases, that is the real gas that we know in real life, they truly, they behave like as though they don't have any attraction for one another. Because when you open a gas container, all of them want to spread away from themselves. They will not want to be as they want to stay together. They will always want to spread from themselves. And also, these gases, if you put them in small container, they will still stay. If you put them in big container, they will still stay. If you reduce this container size, they will still stay. The same amount of gas will still stay in that same small container. But it does not mean that these gases, they don't have a particular size or they don't have a form of attractive force for one another. So there are some conditions that would be met that you find out that these gas, though they are behaving like as if they are calm, but in real sense, they are not calm. In real sense, they are not calm. There are some conditions where you press them to, and they will show their real nature. Ideal gas propose that these gases, can you understand? Do you understand what I'm trying to explain? Hello? Hello, can
Yes,
anybody
I
hear
can
me?
hear you. I understand. Yes, I can hear you.
Okay. Okay. So these ideal gas, they are assumed that they have but they don't have size. They are invisible. They are like spirits. That's what the ideal gas is proposing, that gases are like spirit. They don't have size. They don't have size. Then they also say that these gases, they don't have attraction for one another. That these spirits, they don't like themselves. And no two spirits can fall in love with themselves. Let me say it in that word. Spirits, they don't fall in love with themselves. And spirit, they don't have size. You cannot put spirit in a box and it will not be able to move. It will always move. It can occupy any amount of space that you give it, even if you like. Spirit, they don't have, they don't have body, they don't have size. So for real gases, they said this thing is actually true in most cases. But there are points where you would target these gases or you would change some parameters in these gases and you find out that these gases, it's not that they don't have size, but just that their size is very small. It's not that they don't have size, their size is very, very small, but that their size will be noticeable under specific conditions. Under specific conditions, you find out that, true, these guys, it's not that they don't have size, but they actually have size, but just that you've not brought them to the place where they will be able to show their size. And also, it's not that they don't have attraction for themselves, it's just that they've not brought them to the same area where they would react to themselves or they would behave in that way. I don't know if I'm communicating. So, but that's the idea between real gases and ideal gas. Real gas, they have a particular assumption that they don't have interaction between themselves and they also have no size, no volume. So, but ideal gas, they deviate from real gas in some particular conditions. So now, this theory, the ideal gas assumption led to the formation of what is called the ideal gas equation, which was what I was saying initially, that when you combine the Boyle's law, the Charles law, and the Avogadro's law, it will give you the ideal gas equation. That is that PV equals to nRT. So, but now, there are some conditions where gases then begin to behave differently in case of real gases. So that's when you then see that they then brought in what is known as the Van der Waals equation to correct this deviation, to give a general equation that would still fit in as well. But now the general equation will tell us what the ideal gas equation is saying. But at the same time, it also tell us what the ideal gas equation is not saying. So that's what the Van der Waals equation is saying. That's what the Van der Waals equation was trying to do. It tries to fill up for the places that the ideal gas equation could not explain for. So when gases seem to have high pressure, when there is high pressure between gases, you would find out that gases actually have volume. And when there is low temperature, you would find out that these gases have attraction for themselves. High pressure will show that gases have volume. Low temperature show that gases have attraction for themselves. So this Van der Waals equation is not trying to explain and clarify both conditions or both extreme conditions. I try to say, okay, when you reduce the pressure very well, and the gases will start showing that they have attraction. I don't know. I was mentioning something before. I don't know. It seems like as if you not you kind of got distracted or the call disconnected you. I don't know. Is it your network that was disconnecting you? Hello? 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 What I'm trying to say. If I'm trying to explain now, I'll
I said
explain it
that
forward and
I
probably
wasn't hearing you very clearly. That's why I say you should take it
okay.
again.
Sorry about that. I really wish we were not in
But there
Nigeria. I
is
really
a
wish we were not in
question I
Nigeria because
asked
all this kind of
before. You didn't answer me, and I'm not clear very well
I
there.
answered
I
I
want
answered the
to
question that you
know
asked me
the
before.
gases that are rare gases and those that are ideal gases before we come to Van der Waal question.
Ideal gases, they are hypothetical gas. They are hypothetical gases. They don't really exist in real life. There is no way you can find a gas that you call an ideal gas. But there are gases that behave very close to this hypothetical gas. I don't know how I would use to explain it in a simple term. It's just like as if you're trying to say that human being, every human being, there are some people that they don't usually get angry at all. They can, no matter what you do to that person, the person will never get angry. The person will never get angry. You're swearing at you, this person will never get angry. They say this person is the ideal man. You know, they ever get angry. You know, they ever vex. You know, they ever vex. But that's what they are saying, that person is an ideal man. But now, there is no human being on earth that is that perfect. Because ideal gas, another name for ideal gas is perfect gas. So there is no human being that is really that perfect on this earth that does not get angry. So now, there is an assumption that there's possibly a point where a man will become perfect, that he will not be able to get angry. But in real sense, there's nobody that is that perfect. So now the thing we can see in real sense is that in most cases, some people might have low anger threshold. Some people might get angry very fast. Why some people will not get angry? You press them, but when you press them to a particular point, they would explode because every human being has emotions. So that's how ideal gas and real gas they are being explained. Ideal gases they don't really exist. They're just an assumption. Why real gas is what we know as the normal gas. Why real gas is what we know as the normal gas. I don't know if I'm communicating.
Yes, sir.
So that's just how it is. Just like as you're trying to say, just as you're trying to say, the perfect man is the man that he does not usually get angry. He is 6 feet tall. He is this one and that one. He is that one and this one. That's the assumption that they say this is the sign of a perfect man. This is the sign of a perfect man. But real life, there is no perfect man. There would always be comma in every human being. There will always be comma in every human being. Can you guys hear me?
Yes, I can hear you.
Yes, yes, sir.
Yes, sir, we can
Okay, so
hear you.
that's it. So the real gas, the gas we see every time is actually the gases we see in most cases are actually the ideal real gases. We will not see an ideal gas, but most times real gases can behave like that assumption. We can see a man in real life that he does not get angry fast, but it doesn't mean that that man will not be able to get angry. So ideal gases, they say ideal gases, they don't have size, and ideal gases, they don't have attraction for themselves. But in real sense, some gases can behave like as though they don't have attraction for themselves, and they can behave like as though they don't have size. But there are conditions where you bring these gases to, and they will show that they actually have size and they actually have attraction for themselves. I don't know if it's clear now. So let's move on. So the Van der
Yes,
Waals equation is the equation that tries.
if I'm to rehearse what you said or to show whether I understood you, you said that
Okay.
there is no ideal gas.
Yes.
They are hypothetical gas.
Yeah.
But ray gas are the normal gas we are using.
Yes.
Okay. Can we equate or can we infer that Boyle's law, Charles' law, Avogadro's law, that those gases that are said there, we can infer them to real gases? No, to real
Ideal
gases.
gases. All the gases that I talked about if you look at it under Boyle's law, they gave a condition. Boyle's law, they said at constant temperature. So the Boyle's law will remain true so long as temperature is constant. The Charles law would remain true so long as pressure is constant. Avogadro's law will remain true so long as pressure is constant. So these laws now, they're like portions that tries to predict only the real gas behaviors of gases. They pick a particular portion that real gases behave well and say, this is what gases, this is what I'm trying to talk about. This is what I'm trying to talk about. And when gases are like this, when you do like this, the gas would always behave like this. When you hold pressure down and change volume, temperature would also change. When you hold temperature down and change pressure, volume would also change in the opposite direction. So that's what these things are doing. They are not really trying to tell the general behavior of gases or the general behavior of all gases. They're just trying to tell you that when these things are put in place, this is how gases will behave. When these things are put in place, this is how gases will behave. That's what this Boyle's law, Charles law, and this thing are they try to show. But the law that tries to talk about just ideal gas is the ideal gas equation, and that's PV equals to nRT. PV equals to nRT. So that's the ideal gas equation. So that equation it holds true, as I said, it holds true for most cases. And gases, you can assume that almost every gas, you believe that almost every gas is an ideal gas until you bring them to a particular condition. So you can say that gases are like ideal gas. Most cases that gases will be experienced as they will experience ideal conditions. So that is why you see gases under ideal condition, they will behave like what ideal gas equation is saying. But now, when you start taking them to extremes, these gases will start behaving differently. So that is when this reason for the deviation is what they say, these gases, we thought that these people are perfect people. They're actually not perfect. They're actually real, They are real. They are not perfect. Just that they are calm. They are just calm. They are not perfect. They are calm. I don't know. That's just the idea behind it. So all the gases that we would ever talk, there is nothing like we can never ever find what is an ideal gas. We can never find an ideal gas. We can find gas that behaves close to ideal assumption. So that's just it. So now, as I was saying, I don't know if she's still on the call though. So as I was saying, the Van der Waals equation is trying to balance off for the portions where gases behave differently. And this is the Van der Waals equation. I think I showed it in one of our classes where we said the PV, for the P formula, we had an addition of an extra expression, A bracket N over V all squared. Then for the V side, we have V minus NB. So they introduced two constants, B and A. They introduced B and A, where A is trying to talk about the attractive force constant, and B is talking about the volume constant. So this is the expression that tries to explain all the behavior of gas or the behavior of gases in all conditions, both real and ideal conditions. So now, with all this being said, I don't know if anyone has any question as of now. If you still have another question that maybe you're trying to clarify, just ask your question because I think we are at the end of the class now. Does anyone have any question?
Hello, sir.
Okay.
Hello, sir. Please, I want to ask
Yeah,
a
I can hear you.
question.
Okay, I'm listening.
It's on that avocado law. I thought that avocado law
Okay.
has a constant, like it has a constant number of mole. Where can we apply that constant number of mole?
Okay, for the Avogadro's number, it's when you're trying to check, when they are trying to ask you for the number of atoms present. So then you use the Avogadro's number, that's 6.02 times 10 to the power of 24. So when they're trying to ask you the number of atoms per mole, the number of atoms per mole. So each mole of every single gas or of every single compound contains 6.02 times 10 raised power 24 number of atoms. So every single mole of every atom contains this quantity of atoms. Every single mole of any element contains this number of atoms. Just like as you're trying to say, every single square contains 4 lines. Every single square is made up of 4 lines. So that's how it is. That's how that number is trying to. That's what the number is trying to explain. It's trying to show a constant that tries to tell you that you can use to predict the number of atoms present in different number of moles. So normally this Avogadro's law, it talks about volume and number of moles. So when you're not trying to bring in what they call it, you're not trying to specify. There is an expression that tries to relate number of moles with the number of atoms. So that's when you talk about the Avogadro's number. When you're talking about when you're comparing number of moles and number of atoms, that's when you talk about the Avogadro's number, which it says that one number of mole of every gas is equal to 6.02 times 10 to the power of 24 number of atoms. I don't know whether I made it clear.
Okay, sir. Thank you.
No, sir. No, sir.
Okay, so where is confusing? Hello?
Just what you explained. Can you repeat it, please, sir?
Okay. She asked a question and probably you are not, your call probably was
I said,
distorted.
okay, I understand now. Thank you.
Oh yeah, I get you. She just told me that she did not really understand what I just explained. So I am trying to say that probably she was not really on the call when you asked the question initially. So the question she asked me was, she asked that when do we use Avogadro's number? That is Avogadro's number and we are seeing Avogadro's law. So when do we apply this? So I'm not trying to explain to her that when you talk about Avogadro's number is when they're asking you for number of atoms. So that's when you talk about Avogadro's number. Because Avogadro's number, it is telling you that for every 1 mole of any element, every 1 mole of every element contains 6.02 times 10 raised power 24 number of atoms. So now that's when you use that Avogadro's number. That's when you use that Avogadro's number when they are trying to ask you for number of atoms or trying to ask you a question relating to number of atoms. So now how this thing is just like, it's just like as though you're saying for every square you would always see 4 lines. So that's what it's just trying to say. For every single square you have, you will always see 4 lines. So for every single mole you have, you would always see 6.02 times 10 raised power of 24 atoms. So I don't know whether it's clear now. That I was trying to explain to her.
Yes, sir.
Okay. So now, as I was saying, probably you were not on the call when I talked about Van der Waals force. So I said this Van der Waals force was just, this Van der Waals equation is just a compensation for the ideal gas, or for when gases don't behave like ideal gases. So it's an equation that tries to compensate for conditions when gases don't behave like ideal gases. So this equation is still gotten from the normal PV is equals to nRT. This equation here. This equation here. This equation we are seeing here is still the normal PV equals to nRT. But now, because of some different conditions, so I think if people want to write, I would say you should write somewhere that a gas is said to gases deviate from ideal behavior under the following conditions. I think you should write it down. Gases deviate from ideal behavior under these conditions. So number 1 condition is at low temperature. At low temperature. At low temperature. So you can write column at low temperature, gases tend to reveal their intermolecular force of attraction. At low temperature, gases tend to reveal their intermolecular force of attraction, or they try to show intermolecular force of attraction. That's the first condition. Then the second condition that they use to
They tend to
deviate
do
from
what,
ideal
sir?
behavior is they tend to deviate. What did I even say, sir? At low temperature, gases tend to reveal their what's I even talk, so they tend to reveal their intermolecular force of attraction. At low temperature, gases tend to reveal their intermolecular force of attraction. They tend to reveal their intermolecular force of attraction. So then the second condition that they deviate from ideal behavior is at high pressure. At high pressure, that's the second one. At high pressure, gases tend to show that they have volume, in brackets, size, molecular size, or volume, just put it volume. Just put it volume. So at high pressure, gases tend to reveal that they have volume, although very small in size, although this volume might be very small. Let's put it like that. Although this volume might be very small. Although this volume might be very small.
Hello, sir. Please, I did not get
Yeah?
that point too. Hello, sir.
Okay. Point two is at high
Hello,
pressure.
sir.
Point two at high. Yeah, I can hear you. I'm answering you.
Please,
I said at high
I did
pressure.
not get that, your second point.
Yeah, I'm repeating it. That's what I'm repeating now. I heard what you said. I'm repeating it. So point two is at high pressure, gases tend to reveal their volume. At high pressure, gases tend to reveal their molecular volume. Yes, I think that's the best word that you use. Gases tend to reveal their molecular volume. At high pressure, gases tend to reveal their molecular volume. They tend to reveal their molecular volume. So this is how I used to explain it now. Let me now explain what these things mean. Let's start with point two. You know all this football, all this our ball, normal ball. If we feel this ball we pump this ball very well, or even tire. When you pump this tire very well, no matter how you press it, the tire will not reduce, or the ball will not reduce. No matter how you press it down, it will not reduce, because the gases they cannot shrink themselves anymore. They cannot become compressed more. So although gas is like breeze, it seems like as if they don't have strength. When you compact, when you put pressure on them very well and you force them into a particular point, they will get to a point where they cannot shrink any further. That was trying to show that when you try to shrink gases very well with increasing pressure, it will get to a point where these gases would maintain a standard volume, that they will not be able to go lower than that. And you cannot tell that, okay, this is the size of this. When you have this quantity of gas, this is going to be the size of this volume. This is going to be the volume of this particular gas. I don't know whether that is something that happens in tire. When you pump a tire and you don't pump it fully, all the tire will look completely rounded. Even if you don't pump it completely, it will look completely rounded. But when you apply pressure, the tire will press down to get compressed. But if you get compressed to a point where you cannot compress more than that, it's not touch the wheel, it's compressed to a point where you cannot compress more than that, except the gas is very small inside that tire. But it compress to a level and it's not go down more than that. It will press to an extent, but it's not go down more than that. So that point that it gets that it cannot go down is the volume of that gas that it can contain, that it cannot go any less than that. You get. So that is how he's trying to tell you that when you increase pressure, gas they form something as spirit in B. But if you tight the gas, if you try to lock the gas very well at a particular point, finally you will find out that that gas cannot really escape. It will stay in that point and you cannot press it any further. That was that second principle he's trying to talk about. Or that second deviation, that's where that deviation is coming in. As mean they were ideal gas. Even if you like press the tire, or no matter how you want to be press the tire, you press the tire, the thing will touch itself, or the gas will still be inside. But that's not true. There's a point you will force the gas together and you will not be able to press it any more than that. That's what this thing is trying to show. That's what this thing is trying to tell. That's what that law is trying. That's what this deviation is trying to tell. So in the case of the high temperature or low temperature, if you look at it, liquefied gas, all these are gas that they sell as gas that we use for cooking gas. They are liquefied gas, and normally they are very cold, very, very cold. So these gases would always behave like liquid. they will behave like liquid. And liquid, we said there's a force of attraction between liquid. There's a tiny force of attraction between liquid molecules. So gases will start behaving like liquid when the temperature is very low because they do not have enough energy to keep on moving around. So they will just stay with themselves. Each of the gas molecules will stay with itself and will not run because now the everywhere is very cold. So when cold day, all of them will go and sit down. They'll try to gather themselves together and behave like how liquid will do. So that's just the idea behind it. So at low temperature, at very low temperature, gas molecules will come together and start behaving like liquids. They will come together at very low temperature. They will come together and start behaving like liquid. But now, at high pressure, gases that look like as if they are spirits, they cannot confine, you cannot compress, you cannot hold gas. When you put it in under high pressure in a particular place, you will definitely press the gas and the gas will not go anywhere again. You stay in that particular compacted space. So these are the points that tells that gases are not completely without a volume and they are not completely without intermolecular force of attraction. So that's the explanation for this. I hope it is clear. Hello, I hope it's clear.
Yes, it's clear.
Okay. So we've come to the end of this lesson for today. Come to the end of this lesson for today. So I don't know. I think we are.
Hello, sir.
Yeah.
Hello, sir.
Yeah, I can hear you.
Please, don't vex you, please. I still don't,
Okay.
I can't differentiate between the ideal and the real gas.
Okay, right. Just write now. Just write down now. Write down. I think this will help to just ease of the whole stuff. So ideal gases are gases. Ideal gases are gases that do not have or that does not have intermolecular force of attraction. Ideal gases are gases that don't have intermolecular force of attraction and also don't have molar volume. I don't know if you can still hear me.
Yes,
Hello?
yes, I'm following.
Okay, they don't have intermolecular force of attraction and they also don't have molecular volume. That's ideal gas. While real gases are gases, that seem not to have intermolecular force of attraction. That seem not to have intermolecular force of attraction or molecular volume but are actually found to have molecular force of attraction and molecular volume.
Or molar volume, but
They are assumed
but
not,
they are
where
what?
are you? Just where are you? But they are
I'm
found
at
they are
Britain.
found they are found to have but they are found to have intermolecular force of attraction. When temperature is very low.
And as such, they behave like liquid.
You can put it like that, but just get the thing and the portion I'm trying to work on.
All right, thank you, sir.
When temperature is very low, and also have a molecular volume, and also have molecular volume
Is it
when
intermolecular volume or
pressure,
molecular volume?
any molecular volume,
Okay.
when pressure is very high.
Okay.
So that's I think that's a distinguishment. So if you can memorize this thing, you'll be able to tell. So now this is the difference between real gases and ideal gas. So real gas, they assume that them to behave like ideal gas, they usually brag like ideal gas. But when you bring them to high temperature or to low temperature, they would mellow. When you take them to high pressure, they would also mellow. So they behave like ideal gas in most cases, but when they reach these conditions I mentioned, they would mellow. That is, they will calm down. So but now in real sense, overall, in the whole world, there is no gas that truly does not have this, that does not have molecular volume and also does not have molecular force of attraction. So meaning ideal gases, they don't really exist. So that's just what I've been saying so far.
All right.
Ideal gases don't really exist. So that's it. I think we've come to the end of this lesson. And because of time, I think I have another engagement. That's why I'm kind of trying to hurry up too. So I'll take one more question. Does anybody have any question? One question before